Good day, everyone. Another chemistry of engineering materials that will be considered in the discussion will be the non-ferrous metals. Metals that do not contain iron are called non-ferrous metals. There are many different metals. We choose the right metal, the appropriate metal, suited for a particular job. This tower is made of steel for strength. It is coated with zinc for protection from corrosion. The blades are aluminum because it is light and corrosion resistant. The electric cables are copper because it is a good conductor. There are a variety of properties for non-ferrous metals. Non-ferrous metals are metals that are not iron. Gold is a metal that does not corrode. It is expensive because it is rare. It is rare because it is heavy. The Earth's crust is made mainly of light elements. Most of the gold are found close to the center of the Earth. Gold is very malleable. Gold can be beaten into a very thin foil and used to coat statues or jewelries. Even after thousands of years, it is still as shiny as ever. Gold is used in jewelry. Gold is usually mixed with silver or copper to strengthen it and make it cheaper. Gold is the best conductor of electricity. Connections work every time because there are no oxides coating to block the flow of electricity. Silver is similar to gold. Silver is also used in decoration, jewelry, and silverware. Silver is easily tarnished by hydrogen sulfide in air, and it needs to be polished most often. Silver is cheaper because it is not much needed in as much as making films or coatings. In jewelry, silver had been replaced by stainless steels. Silver soldering involves and makes use of a rod made of silver, copper, and zinc. Silver soldering is used to join copper parts. Let's talk about copper. Copper is similar to gold and silver. It is soft and a good electrical conductor. It is the third most used metal after iron and aluminum. Copper is the metal choice for most wirings of electrical machinery, appliances, and power supplies. It is also used for household water supply as it does not corrode in water. Copper could easily be bent to change direction. Copper is easy to join just by soldering. What about brass? Brass is 70% copper and 30% zinc. Brass is an alloy of copper and zinc. It has a distinctive color and it's malleable so it can be worked into complex shapes. Brass is harder than copper, so it performs better. This is important for products with moving parts. Brass is highly corrosion resistant. This is a plus factor for a product that is constantly subjected to the moisture and salts in saliva. A lower copper content produces brass that is harder. This type of brass is used for top handles, windows, and door fittings. They are usually made by casting. These ancient China statues are made of bronze. A bronze is an alloy of copper and tin. Bronze is easy to cast and can be left outdoors without corroding. Bronze is strong. It was used to make tools and weapons such as spears and swords. This metal brought about the Bronze Age. Bells are made of bronze because of the sustained notes it produces and its corrosion resistance. Bell metal has a high tin content. For every 4 parts of copper will be 1 part tin. These two sections of the bike frame are braced together with bronze, which was melted on the surfaces. The heat of welding is used to melt bronze on the sections of this bike. Bronze strengthens the different sections of the bike. The bronze cannon has lower tin content. It's only 10%. Because bronze is highly resistant to corrosion and very hard wearing, bronze is used for gears and bearings in machinery. If proper proportions of lead and phosphorus will be added to bronze, the metal even becomes harder. What about zinc? Zinc is a soft metal and relatively cheap. Zinc is not easily corroded. Zinc has low melting point. Because zinc has low melting point, it allows other metals or steels in a hot dip galvanizing process. Zinc is mainly used to prevent steels from rusting. Zinc forms oxides at the surface of the steel that serves as coating and protection for the steel. The control engineer in this plant monitors and adjusts the parameters. Parameters for the coating of steel with zinc and aluminum alloy. What is tin? Tin is another metal used in ancient times. Tin is used as a corrosion-resistant coating that gives a silver finish. Tin is also used mainly as a protective coating on steel like these tin cans. Nowadays, Cans are usually coated with a clean finish of tin coating. Solder is an alloy of tin and lead. It is useful because of its low melting point. Aluminum. Aluminum alloys are used in aircraft construction because weight is critical in the design of different aircrafts. The leading edge of the wing flaps of an aircraft is made of an aluminum alloy with 3% copper. Because aluminum is corrosion resistant, it can be used without painting, plating, or even coating. The natural oxide coating can be thickened by a process that is called anodizing to give a smoother, hard-wearing surface. Dyes can be added to produce colored finishes. One of the major uses of aluminum alloy is for drink canning. Aluminum is highly ductile. This means that the sides and base of the aluminum is made only in one piece. They are simply drawn down and pressed out of a flat sheet. Aluminum cans are light, making transportation cost very low. Because aluminum is malleable, we could hold a sheet that holds its new shape. Aluminum has a very low melting point. Once aluminum is molten, the oxide coating can no longer protect it, so it then oxidizes very easily. Aluminum is expensive because it needs a lot of energy to process it from the aluminum ore called bauxite. That is why aluminum cans are eagerly recycled, and it is highly recommended. What about nickel? Nickel is harder than iron, but too brittle to be used on its own. Nickel is usually alloyed with softer metals like copper and aluminum to make coins more hard-wearing. These coins look like silver, but they are actually copper-nickel alloy. In the United States, a nickel is a 5-cent coin. Nickel is alloyed with iron, chromium, and carbon to produce stainless steels. What about titanium? Titanium is a fantastic metal. Titanium has the density of aluminum and the strength of a steel. Titanium does not corrode easily. Titanium is used in military, aircraft, and climbing equipment, where weight and strength are critical and price is not. Titanium is used inside the human body to strengthen and support bones. Titanium is very difficult to cut. Titanium has to be cut using a water jet. A water jet with abrasive in it. There are special tools that are designed to cut titanium. What about magnesium? Magnesium is the lightest of the common metals. Magnesium is also used in the manufacturing of rims of tires found in vehicles. Rims are also coated. They may be coated with special type of metals. Magnesium is usually alloyed with aluminum to produce high-quality anti-corrosion wheel mags. Magnesium and aluminum make the car wheel mags lightweight. How do we choose a metal for a particular design? The main disadvantage of steel is that it rusts. It needs to be protected by a coating that does not corrode. Examples are paints and non-ferrous metals. Roofing iron is coated with zinc. It does not corrode in air and water. If the surface is meant to be shiny and wear resistant, chromium is the best choice. Nickel is similar to chromium and almost as hard. In nickel and chromium plating, a series of chemical buds clean the surface before electroplating process deposits a thin layer of nickel. If only certain parts are to be plated, the rest must be coated with wax. The thickness of the coat can be controlled by the length of time and the plating continues. Copper is a good conductor. It spreads the heat evenly over the bottom of the pot. But copper is too soft that it may deform at high temperatures. A good design is to have a stainless steel body with a copper bottom. Copper reacts with carbon dioxide in the air to form a green compound called copper carbonate. As this process takes a few years, manufacturers nowadays produce this green color in the factory. Aluminum oxidizes easily, forming a strong layer that protects the aluminum below. This stops any further corrosion. This is one reason why aluminum is used outdoors. Chromium and nickel oxidize in air, but the oxide layer is clear, preventing any more oxygen reacting with the metal. Many other non-ferrous metals are corrosion resistant. Their oxide layers are impervious to oxygen. This is why zinc and aluminum are corrosion resistant. Let's consider electrical conductivity. Generally, metals are all good electrical conductors, but some are better than others. Let us consider three circuits with a copper wire, aluminum wire, and steel wire. We switch between the circuits. Apply the same voltage to each circuit. This is the reading for the resistance of steel wire. This will be the reading for the resistance of the aluminum wire. And this will be the reading for the resistance using copper wire. This will be for the steel, aluminum, and the copper. We observe copper with the lesser resistance. Copper shows the least resistance. It means copper conducts electricity better than aluminum and steel. Even though copper is the best conductor, many high voltage power lines are aluminum because aluminum is lighter than copper. So the tower will not hold as much weight. Aluminum is cheaper than copper. What about electrochemical properties? When metals are mixed together, it is possible to produce a trouble. Joining copper and zinc can have electrochemical reaction. It will generate electricity. It is useful in batteries, but to your job, you can have corrosion. Plumbers prevent electrochemical reaction by using Teflon to insulate copper and zinc. There are instances when we can join metals. You can use steel bolts on aluminum, zinc, or chromium because the oxide layer prevents the electricity to flow. Some combinations work and others do not. These are only few of the many factors you have to consider next time you choose a metal for a particular job. Before the Iron Age, most iron came from space. Iron makes up much of our planet's core, and it is the fourth most abundant element in the crust. Getting iron to use it to make tools has not always been a simple process. Most iron is packed away in ore, and you have to know how to smelt it to produce the metal. Iron is known for its strength and workability. Humans didn't really master the process to produce at a large scale until around 1200 BC. But once they did, the next period of human history is known as the Iron Age for a reason. However, iron does appear in the archaeological record in the early Bronze Age. An Egyptian pharaoh, King Tutankhamun, who died in 1324 BC, was buried with an iron headrest, bracelet, and a dagger. For a long time, it was thought that some civilization somewhere had managed to smelt iron earlier, resulting to ancient artifacts. There is another way to get iron. one that is literally out of this world. Some ancient civilizations did appear to make the connection. Egyptian hieroglyphics referred to iron as being from the sky, and Confucius is said to have made the first description of the first meteorite fall. Who was Confucius? He was born in 551 and died 479 BC. He was a Chinese teacher, editor, a politician, and a philosopher of the spring and autumn period of Chinese history. The philosophy of Confucius, also known as Confucianism, emphasized personal and governmental morality, correctness of social relationships, justice, and sincerity. His followers competed successfully with many other schools during the Hundred Schools of Thought era, only to be suppressed in favor of the legalists during the Qin dynasty. Both the streak in the sky and the rock on the ground in 645 BC are recently made map of 500 years of meteor record showing that the West doesn't really take notice of any meteorite fall. Between the 16th century and the 19th century, most Western astronomers shared Isaac Newton's assumption that rocks didn't simply fall from the sky. Who is Isaac Newton? He was born January 4, 1643 and died March 31, 1727. Isaac Newton was a physicist, a mathematician who developed the principles of modern physics, including the laws of motion, and is credited as one of the great minds of the 17th century, a scientific revolution. In 1687, he published his most acclaimed work, Philosophia Naturalis Principia Mathematica, Mathematical Principles of Natural Philosophy, which has been called the single most influential book on physics. In 1705, he was knighted by Queen Anne of England, making him Sir Isaac Newton. It follows, John Venn explains that it took Western archaeologists too long time to understand that ancient peoples could make the connection between the astronomical and earthly phenomena. John Venn was born August 4 of 1834 and died April 4 of 1923. He was an English mathematician, logician, philosopher who noted introducing the Venn diagram that is used in set theory, probability, logic, statistics, competition math, and computer science. In 1866, Venn published The Logic of Chance, a groundbreaking book which espoused the frequency theory of probability, offering that probability should be determined by how often something is forecast to occur as opposed to educated assumptions. It has been taught, for example, that the iron used by the Egyptians came from an early smelting industry in Anatolia, where the Hittites may have started to work on iron in as early as 1500 BC. The meteorite hypothesis has been raised consistently for all the early iron objects in the archaeological record, and in several cases this had been proven through scientific analysis, according to a research study by Marcus Martin and Torres, an expert on the archaeology and metallurgy at the University of London. However, there were some uncertain cases where the evidence was less clear. One of the main challenges was to come up with a way to study the chemical composition of the artifacts without damaging them. It was concluded that in ancient times, iron was 10 times the price of gold. That was why meteorites were not just found but actively searched for. Iron was just like diamonds today. Iron was a highly valuable material used only for the jewels or tools for the king. The theory is that in the ancient times, people were going mad to look for meteorites. There are rare metals found in our planet or in the universe. Scandium is a chemical element with symbol Sc and atomic number 21. A silver-white metallic D-block element, it has historically been classified as a rare earth element together with yttrium and the lanthanides. It was discovered in 1879 by spectral analysis of the minerals euxenite and gadolinite from Scandinavia. Yttrium is a chemical element with symbol Y and atomic number 39. It is a silvery metallic transition metal chemically similar to the lanthanides and has often been classified as a rare earth element. Yttrium is almost always found in combination with lanthanide elements in rare earth minerals and is never found in nature as a free element. Yttrium is the only stable isotope and the only isotope found in the Earth's crust. Lanthanum is a chemical element with symbol La and atomic number 57. It is a soft, ductile, silvery white metal that tarnishes rapidly when exposed to air, and it is soft enough to be cut with a knife. It is the eponym of the lanthanide series, a group of 15 similar elements between lanthanum and lutetium in the periodic table, of which lanthanum is the first and the only prototype. It is also sometimes considered the first element of the sixth period transition metals and is traditionally counted among the rare earth metals. Cerium is a chemical element with symbol Ce and atomic number 58. Cerium is a soft, ductile, and silvery white metal that tarnishes when exposed to air. It is soft enough to be cut with a knife. Cerium is the second element in the lanthanide series, and while it often shows the +3 oxidation state characteristic of the series, it also exceptionally has a stable +4 state that does not oxidize water. It is also traditionally considered one of the rare earth elements. Cerium has no biological role and is not very toxic. Praseodymium is a chemical element with symbol Pr and atomic number 59. It is the third member of the lanthanide series, and it is traditionally considered to be one of the rare earth metals. Praseodymium is a soft, silvery, malleable, and ductile metal, valued for its magnetic, electrical, chemical, and optical properties. It is too reactive to be found in native form, and pure praseodymium metal slowly develops a green oxide coating when it is exposed to air. Neodymium is a chemical element with symbol Nd and atomic number 60. It is a soft silvery metal that tarnishes in air. Neodymium was discovered in 1885 by the Austrian chemist Karl Auer von Welsbach. It is present in significant quantities in the ore minerals of monazite and bastnasite. Neodymium is not found naturally in metallic form or unmixed with other lanthanides, and it is usually refined for general use. Prometium is a chemical element with symbol Pm and atomic number 61. All of its isotopes are radioactive. It is extremely rare, with only about 500 to 600 grams naturally occurring in Earth's crust at any given time, and one of only two such elements that are followed in the periodic table by elements with stable forms, a distinction shared with technetium. Chemically, prometium is a lanthanide. Prometium shows only one stable oxidation state, and that is positive 3. Samarium is a chemical element with symbol Sm and atomic number 62. It is a moderately hard silvery metal that slowly oxidizes in air, being a typical member of the lanthanide series. Samarium usually assumes the oxidation state positive 3. Compounds of samarium are also known, most notably by the monoxide SMO, monochalcogenides SMS, SMSE, and SMTE, as well as samarium 2 iodide. Europium is a chemical element with symbol Eu and atomic number 63. It was isolated in 1901 and is named after the continent of Europe. It is a moderately hard silvery metal which readily oxidizes in air and water. Being a typical member of the lanthanide series, europium usually assumes the oxidation state positive 3, but the oxidation state positive 2 is also common. Gadolinium is a chemical element with symbol Gd and atomic number 64. Gadolinium is a silvery white, malleable, and ductile rare earth metal. It is found in nature only in oxidized form, and even when separated, it usually has impurities of the other rare earth metals. Gadolinium was discovered in 1880 by Jean-Charles de Marignac, who detected its oxide by using spectroscopy. It is named after a mineral, gadolinite, one of the minerals in which gadolinium is found, itself named for the chemist Johann Gadolin. Terbium is a chemical element with symbol Tb and atomic number 65. It is a silvery white, rare earth metal that is malleable, ductile, and soft enough to be cut with a knife. The ninth member of the lanthanide series, terbium is a fairly electropositive metal that reacts with water, evolving hydrogen gas. Terbium is never found in nature as a free element, but it is contained in many minerals including cerite, gadolinite, monazite, cenotime, and euxenite. Dysprosium is a chemical element with symbol Dy and atomic number 66. It is a rare earth element with a metallic silver luster. Dysprosium is never found in nature as a free element, though it is found in various minerals such as cenotime. Naturally occurring dysprosium is composed of 7 isotopes, the most abundant of which is Dy dysprosium. Holmium is a chemical element with symbol HO and atomic number 67. Part of the lanthanide series, holmium is a rare earth element. Holmium was discovered by the Swedish chemist Per Theodor Cleve. Its oxide was first isolated from rare earth ores in 1878. The element's name comes from Holmia, the Latin name for the city of Stockholm. Erbium is a chemical element with symbol Er and atomic number 68. A silvery white solid metal. When artificially isolated, natural erbium is always found in chemical combination with other elements. It is a lanthanide, a rare earth element originally found in the gadolinite mine in Ytterby in Sweden, from which it got its name. Thulium is a chemical element with symbol Tm and atomic number 69. It is the 13th and the third last element in the lanthanide series. Like other lanthanides, the most common oxidation state is positive 3, seen in its oxide, halides, and other compounds. Because it occurs so late in the series, however, the positive 2 oxidation state is also stabilized by the nearly full 4F shell that results. Ytterbium is a chemical element with symbol Yb and atomic number 70. It is the 14th and penultimate element in the lanthanide series, which is the basis of the relative stability of its positive 2 oxidation state. However, like other lanthanides, its most common oxidation state is positive 3, as in its oxide, halides, and other compounds. Lutetium is a chemical element with symbol Lu and atomic number 71. It is a silvery white metal which resists corrosion in dry air, but not in most air. Lutetium is the last element in the lanthanide series. It is traditionally counted among the rare earth metals. Lutetium is sometimes considered the first element of the 6th period transition elements, although lanthanum is more often considered as such. So, it's a matter of knowledge and a matter of the right choice in choosing the right metals for our design. Metals always play an important role in the field of engineering. Understanding metals better will bring you as an engineer ahead of time. Good day, everyone.